Hello friends, welcome to our course on General Relativity. This is Einstein's theory of gravitation, which was built on the foundation of his special theory of relativity, and was based on his insight, now known as the principle of equivalence. We shall follow the same path in this course, starting with a complete introduction to special relativity, which is the theory of flat spacetime and inertial observers. Then using the principle of equivalence to introduce the effects of gravity. Roughly speaking, the principle of equivalence implies that an observer in an accelerated elevator will feel a force that is indistinguishable from gravity. The prerequisites to this course is a working knowledge of calculus and basic Newtonian mechanics. No prior knowledge of special or general relativity is required. We shall attempt to develop everything from scratch, deriving any equations we need and going through all the intermediate steps. Hopefully, this will allow you, my viewers, to follow these lectures in real time. These are the references for this course. Our approach is closest to the first book by Steven Weinberg. This is how a particle physicist views general relativity, as just another field theory. The emphasis is on the principle of equivalence. The geometric aspects of curved spacetime are downplayed. Although it includes a chapter on differential geometry, all calculations are done using tensor components. This is a book where you'll see a lot of results developed from first principles. Weinberg dived directly into the physics and introduced the mathematics only when necessary. The second book is more recent and has a broad coverage of all the modern topics. The approach is clear and straightforward, suitable for an undergraduate, while Weinberg's book is more graduate level. The last book is derived from the lectures of Bryce DeWitt, who was well known for his ability to perform very difficult calculations in general relativity. You'll find plenty of that in this book, worked out in great details. Problems and solutions are also included in this book. You can find the links to these books on Amazon in the description below. Let's start with special relativity. This topic will be covered over a few videos. For the first part, our focus is on the inertial observers. The quantitative way in which an observer makes any reference to events in space-time is through a reference frame or coordinate system. There are 1 time and 3 spatial coordinates. To collect all these as different components of the same point in space-time, we multiply t by the speed of light to give it the same units of length as the rest of the coordinates. For now, c is just a conversion factor, converting time to length. We have assumed that this is a rectilinear coordinate system, such that a free particle, under no influence of any force, will travel along straight-line trajectories at constant velocities. We have in fact just described the definition of an inertial reference frame attached to an inertial observer. This will be made more concrete in a moment. Later on, we shall move on to more general coordinate systems. The standard convention is that the Greek indices will run from 0 to 3, labeling all 4 spacetime coordinates, while the Latin indices are restricted to the spatial components. Let this reference frame be attached to an inertial observer O. Of course, there could be any number of inertial observers, another could be O'. We shall assume all these observers to be equally valid observers of events in space-time. None of them are special. Both of these are rectilinear coordinate systems, although they may not have the same orientations. Now let's look at how these two coordinate systems are related. This can be done by a coordinate transformation. Let's assume this function to be continuous and invertible. Now we introduce a law of nature, which is one of the defining principles of special relativity. This states that the speed of light must be the same in any inertial reference frame. This is an empirical fact which we shall treat as a postulate. An inertial reference frame is simply a non-accelerating frame. Let's see how this law constrains the transformation function above. Suppose light travels through an infinitesimal displacement in spacetime. Let's calculate its speed in both reference frames. In the frame of O, the square of the speed of light is given by, which is just the dot product of the velocity with itself. Here we introduce the Einstein's convention, where repeated indices are summed over all its possible values. This must be equal to c squared. Another way to write this is to contract the velocities with the Kronecker's delta, which is defined by the following. By the principle of relativity, the same has to hold for observer O'. We can write this in terms of differentials. Ct is just x0. Let's write this in terms of the four-dimensional displacement by introducing the matrix eta. This matrix is diagonal, with the value -1 for the time component and +1 for the spatial ones. Eta is what is known as a metric. More specifically, it is the Minkowski metric. A metric provides us with a measure of distance. This equation must hold for any coordinate system. Let's define this quadratic form as the square of the distance associated with this displacement, and it is invariant under the change of reference frames. All observers should agree on spacetime distance. Therefore, the constancy of the speed of light across all inertial reference frames implies that light travels along trajectories that are made up of infinitesimal displacements which have zero length. Up till now, we are only talking about the spacetime displacement made by light. But we could apply this idea of an invariant distance to any spacetime displacements. ds squared in general may not be zero. A spacetime displacement with ds squared equals 0 is known as a light-like displacement, while a displacement traveled by a particle with velocity less than the speed of light is known as a time-like displacement. This has ds squared less than 0. This result is easily seen by expanding out the expression. It is called a time-like displacement because in order for ds squared to be less than 0, the time part has to dominate. It is important to note that ds squared is merely a notation for eta mu nu, contracted with dx mu dx nu, since it is possible for it to be negative. On the other hand, if the spatial part dominates, we have a space-like displacement. Any particle traveling across such a displacement will be traveling faster than the speed of light. As we shall show later in this lecture, such a possibility will lead to causality violations or paradoxes. Now let's examine how the invariance of ds² between two reference frames might constrain the coordinate transformation connecting them. The infinitesimal spacetime displacement dx' is related to dx by the simple rules of partial derivatives using the function above. In order to properly compare both sides of this equation, let's change the dummy indices on the left-hand side such that they match the right-hand side. And we end up with this equation. Notice that eta on either side are constants. Naively, this would suggest that these two derivatives should also be constants in spacetime. Let's try to verify this in a general way. We just have to show that any second derivatives of the transformation functions have to be zero. If they satisfy this equation, let's apply an arbitrary derivative with respect to x on both sides of the equation to generate second derivatives. This is our first equation. We would like to isolate the second derivative above, which is in the first term of equation 1. Notice that the second term is symmetric with respect to the indices gamma and beta due to the properties of partial derivatives. We might be able to remove this term by subtracting from equation 1 another equation with the indices gamma and beta switched. This gives equation 2. But now we have gained a new term. Let's just press on. Now the second term in equation 2 is symmetric in the indices alpha and beta. Let's try and remove this term by using the same procedure. Which gives equation 3. All three equations have identical first terms. Notice also that the second term of both equations 1 and 3 are identical, differing just by a minus sign. This is so because the matrix eta is symmetric. The second terms should cancel if we sum the two equations. As you can see, we are almost there. Notice that this derivative can be inverted by contracting with the derivative of x with respect to x prime. The effect of this Kronecker delta is to select from the sum over the dummy index nu of eta, the index rho. The matrix eta is also invertible and is its own inverse. Note that here we have used eta with both indices raised. this is really the same matrix. We have not yet attached any significance to the raising and lowering of indices. This will come later. Presently, this is just a notation. For better comparison, let's change the dummy index mu to nu. Now removing eta with its inverse. And we have our result. Since all the second derivatives are zero, this implies that the first derivatives are constants, which is represented by the matrix capital lambda. We can integrate this to give a linear relation between x prime and x. A is the constant of integration. This means the origin in the coordinate system x corresponds to x prime equals A. Let's substitute our result back into the equation, which comes from the invariance of spacetime distance. A is completely unconstrained by this equation. This relation between x and x prime is known as the inhomogeneous Lorentz transformation or the Poincare transformation. Often, we shall refer to the matrix lambda as the Lorentz transformation. Now, let's solve for lambda using the invariance equation. First, we could relate the relative velocity between O and O prime to the components of the matrix lambda. This red dot is a fixed spatial location in the coordinate system of O, while it is moving with respect to O prime. Therefore, the red dot undergoes only displacement in time in the frame of O. This corresponds to a displacement both in space and time with respect to O prime. We can use this space-time displacement to calculate the velocity of the red dot with respect to O prime. Since the red dot is stationary with respect to O, v is therefore also the velocity of O with respect to O prime. Now we can relate the velocity v to the matrix elements of lambda using these three boxes. The Lorentz transformation gives us the displacement of x prime in terms of x. A drops out since it is a constant. Expanding the right-hand side of this equation, and using the fact that the spatial displacement in O frame is zero. We can then use the space-time displacement of x prime to calculate the velocity, like we did in the blue box. This allows us to relate the matrix elements of lambda to the velocity of O with respect to O prime. This is our first result. But we haven't yet started solving the equation in the red box. This is just to introduce the physical parameter v into the definition of lambda. Now we solve for lambda by breaking down the equation in the red box into three parts. The first equation corresponds to both of the three indices being the time component. We can substitute the result in the blue box into the second term on the right-hand side. Thus, we have the result for lambda 0, 0. V squared is just the square magnitude of the spatial tree-vector V. For lambda 0, 0 to be a real number, V has to be less than the speed of light. So the relative speed between any two inertial observers has to be less than the speed of light. This is consistent with our earlier statement that any physical particle cannot travel faster than the speed of light. Notice that we can take either the positive or the negative square root. For the positive branch, lambda 0, 0 can take values between 1 and infinity, for V ranging between 0 and c. Whereas for the negative branch, lambda 0, 0 is between minus infinity and minus 1. Notice that these two domains are not connected. This means if lambda 0, 0 is to be a continuous function of its parameters, it must live entirely on a single branch. We shall choose the positive branch so that the matrix lambda could be continuously connected to the identity transformation. Let's explain what this means. First of all, note that the invariance equation can be viewed as a matrix equation. The right-hand side consists of matrix multiplications. The indices of the matrices in the matrix multiplication are contracted in a sort of chain. The first pair of indices on the right-hand side fits the pattern, while for the second pair, we have to introduce the transpose of the lambda matrix. In a special case, where the Lorentz transformation just relates the coordinates in a single frame back to itself, lambda is just the Kroneker's delta, which is the identity matrix. For this case, the 0, 0 component of lambda is just 1. This happens to lie within the domain of the positive branch and corresponds to the case of V equals 0, where O is stationary with respect to O prime. This is what we mean when we say that lambda is continuously connected to the identity. Therefore, by choosing the positive branch, we are studying a family of inertial observers that could be connected by continuous accelerations. This expression is often notated by gamma. Let's now look at the invariance equation that corresponds to one time and one spatial index. Since eta is a diagonal matrix, the left-hand side is just 0. For lambda I0, we can plug in the result below. Lambda 0, 0 can be factored out. This gives lambda 0j in terms of lambda ij, which is yet to be solved. Notice that since the equation in the red box is symmetric with respect to the indices alpha and beta on both sides, We need not consider the case of alpha equals to j and beta equals 0. Now for the last set of equations, with alpha equals j and beta equals k, both are spatial indices. From the definition of eta, the left-hand side is just the Kroneker's delta. These are the equations that should constrain lambda ij, the remaining unsolved components. As you can see, it is not so straightforward to tackle this equation directly. So it would make sense to find out beforehand what are the numbers of independent parameters that the matrix lambda should contain, given the constraints in the red box. Let's do some counting. Let's first count the number of constraint equations. The matrix represented by the bracket is a 4x4 symmetric matrix. So the number of independent components is 4 square minus 4 diagonal terms, and dividing by 2, this would give the upper off-diagonal terms of the matrix. Then add the diagonal terms. So we have 10 independent equations. The number of parameters of lambda before applying any constraint is just 16. Therefore, the number of independent parameters is just 16 minus 10. Thus, the number of degrees of freedom in lambda ought to be 6. With this figure as a guide, we can then look for simple special cases of lambda, which are obviously independent transformations from each other. Then make sure that their parameters tally up to 6. When that is achieved, any Lorentz transformation which is connected to the identity could then be expressed as combinations of just these simple transformations. We would then have the complete solution of lambda. For the first case, let's consider the velocity only along the first axis. This immediately simplifies lambda I0. The only non-zero component is lambda 1, 0. Now we have to make a conjecture about lambda ij. First notice that delta ij can be broken down into 3 parts. Each term is a projector of the component along an individual axis. Lambda ij would be equal to delta ij for the trivial case of the identity transformation where v equals 0. As with velocity, we can single out the first axis by introducing a new parameter lambda 1, 1. This would be the deviation from the v equals 0 case. Let's substitute this conjecture into the expression for lambda 0j. Only these two terms are relevant for the equation above. Let's substitute them into the equation. Let's verify that these two expressions are equal. I would like to remind you again that at this stage, it doesn't matter if the indices are up or down, it is merely a notation. This should reduce much confusion in our calculations. As we have said earlier, these deltas are actually projectors along each spatial axis. Let's verify this. A projector acting on itself will return the same projector. A projector acting on another projector along an orthogonal axis will give 0. These properties can be summarized in this equation. Notice also that all the projectors are symmetric in their indices. This makes it apparent that the equation above has to be true. Now we can solve this equation for lambda 1, 1. These two terms can be combined. The delta on the left-hand side can also be expressed in terms of projectors. And there's a cancellation between both sides. This implies again, there are two branches to the square root. As before, we take the positive root so as to be continuously connected to the identity. And so, we have all the non-zero components of lambda for the special case of V pointing along the first axis. This is known as the Lorentz Boost along the first axis. Let's see explicitly how this relates the displacements delta x and delta x prime. First, for the time displacement, we have now the displacement along the first axis. From the last two terms of lambda ij, these last two terms are 0. And we can substitute in the results for these two elements. For the displacements along the second and third axes, the only relevant non-zero components are lambda 2, 2 and lambda 3, 3. The displacements of x and x prime agree along these two axes. This means the observers O and O prime will agree on the displacements which are perpendicular to the velocity. The Lorentz Boost along the first axis only mixes the time and the first spatial components of the spacetime displacement. We can represent this mixing by the following matrix equation. And in 4 dimensions. The second and third components are unchanged by this identity submatrix. We denote this matrix as lambda 0, 1, since it only mixes the 0 and 1 components. This transformation carries only one parameter, v1. Note that our earlier results below are general and must hold for any Lorentz transformation connected to the identity, while v and this form for lambda ij is specific to the boost along the first axis. It is apparent that we can get the Lorentz boost along the other two axes with only slight modifications to our result. By changing the direction of v and inserting the lambda parameter in the right places. You can easily verify that these are Lorentz transformations which satisfy the last invariance equation by retracing our steps. Again, it is most instructive to express lambda ij in terms of the projectors along the three spatial axes. This will help us derive the Lorentz boost along an arbitrary direction. Observe the common features of all these boosts. Notice that gamma is attached to the projector along the direction of the velocity, while the other two projectors along the two perpendicular axes have coefficients 1. Thus, for the Lorentz boost along an arbitrary direction, we can try the following solution. Gamma is attached to the projector along the velocity, and the second term is the projector into the perpendicular directions, which can be expressed as the identity minus the projector along v. This solution automatically includes the solutions along the individual spatial axes. But let's check that this is really a Lorentz transformation and satisfies the invariance equation. The rest of the matrix elements of lambda can be derived by the general results below. What we need to do now is to plug in these two expressions into the red box above and verify that the equation is indeed satisfied. Our first step is to write down a suitable expression for the projector PV. What about this? As you can see, acting on a vector parallel to V returns the same vector as required, while acting on a vector perpendicular to V gives 0. So this is indeed the required projector. Now let's proceed with our substitutions. We will need lambda 0j. Notice that in this expression, lambda ij is contracted with V, therefore the perpendicular projector just drops out. Thus we have the result for lambda 0j. Now we are ready to calculate the right-hand side of the equation. The second product is easier if we use the properties of the projector. The result is just adding a square to gamma. Consolidate these two terms. Gamma squared cancels with its inverse. These two terms cancels. And we have our result. Thus we have verified that this test solution does indeed lead to a Lorentz transformation. Here's a summary of our results for the general Lorentz Boost. This is not too difficult to remember. First, you need to know the definition of gamma. Furthermore, the mixed indices components are basically identical, with the spatial index carried by the velocity. And for components with two spatial indices, this adds a factor of gamma to the component along the velocity, while it acts like the identity operator for the perpendicular directions. The Lorentz Boost carries three parameters, which means we are still short of three parameters from a complete description of Lorentz transformations that are connected to the identity. These will be covered by spatial rotations in 3 dimensions. R is the usual 3x3 rotation matrix, which rotates the familiar spatial 3 vectors. Incorporated into the usual 4x4 lambda matrices, the time component is left alone, so lambda 00 is just 1. The purely spatial elements are just those of the 3x3 rotation matrix. Recall that R is an orthogonal matrix, which means its inverse is equal to its transpose. The mixed indices elements are all 0. We can easily show that a rotation is a Lorentz transformation by looking at the matrix representation of the invariance equation. For simplicity, we have abbreviated the 3x3 identity matrix by this notation. This is the matrix eta. Let's apply the matrix in the yellow box on the right-hand side of eta, and the transpose on its left, which gives by the fact that R is an orthogonal matrix, we get back eta. Thus spatial rotation is a Lorentz transformation. Since the rotation is described by a rotation vector, which carries 3 real components, we have made up all the parameters of the Lorentz transformations. Thus all Lorentz transformations that are connected to the identity can be expressed as a composition between a Lorentz boost and a rotation. With the suitable choice of parameters. Just to be clear, in so writing, we are using the fact that if lambda 1 and lambda 2 are both Lorentz transformations which satisfy the invariance equation, then so do their composition. Alternatively, to make the completeness of our results more convincing, we can express a general Lorentz transformation in this way, where the independence of all the transformations are made more apparent, since they are each mixing different pairs of components. Notice that there are exactly 6 transformations, each carrying a real parameter, making up all the possible degrees of freedom. Here's a sample of what these matrices look like. We are only showing the 2-dimensional subspace in which non-trivial mixing of components have occurred. A brief remark on the relation between these two representations. Notice that for rotations, we can actually represent any arbitrary rotation in terms of the compositions of rotations about the individual axes, with suitable choices of parameters. The composition of rotations can never result in a Lorentz boost since they do not involve any transformation in time. On the other hand, it is not true that any Lorentz boost can be decomposed into the boost along three independent axes. Some rotation would have to be involved. We shall prove this in the next lecture. But putting together rotation and boost, these two representations are equivalent. To prove that we really have a complete solution of Lorentz transformations in terms of boosts and rotations, the most rigorous way to do this is by dealing with the Lorentz group. This deserves its own video in the future. As an aside, combining two Lorentz boosts which velocities are not along the same axis will give us a resulting Lorentz boost with an additional rotation. This rotation occurs in the plane of V1 and V2 and is known as the Wigner's rotation. We shall prove this result in the next lecture, which will be important for our discussion on accelerated observers. The Lorentz transformations that we have been talking about belongs to the category of proper Lorentz transformations. These are essentially transformations that are connected to the identity and leads to two properties. The first is that the 0,0 component of the transformation must be greater or equals to 1. A question then occurs if this property is preserved by composition. That is, if two Lorentz transformations, lambda 1 and lambda 2, both possess this property, would this be true for their composition, lambda 3? The answer is yes. And we can see this by deforming the transformation continuously. This is because from the invariance equation, the only other possibility is for the 0,0 component to be less equal to 1, which is disconnected from the other case. And if we define lambda 3 prime by the composition of the identity matrix and lambda 2, this matrix can be deformed continuously into lambda 3 by deforming the identity matrix into lambda 1. And it is obvious that lambda 3 prime satisfies the property in the red box because lambda 2 does. This means the 0,0 component of lambda 3 would also be greater or equals to 1, since it must be a continuous function of its parameters and could not jump discontinuously to the range less equals to 1. So the first property of a proper Lorentz transformation must be preserved by composition. This is a necessary feature for this group of transformations to be closed. The second property is that its determinant is equal to 1. This is also preserved by composition. Since the determinant of a product is equal to the product of determinants, this is an elementary fact in matrix analysis. What does our invariance equation say about the determinant of lambda? The determinant of eta cancels on both sides of the equation. And since a matrix and its transpose have the same determinant, we have, which implies that a Lorentz transformation can have determinant of either 1 or minus 1. These two possibilities are discontinuous. And since the proper Lorentz transformations are those that are connected to the identity by the continuous variation of their parameters, they must share the same determinant as the identity matrix. As the determinant is a continuous function of the parameters of the matrix, the function in this case is just a constant. These are the two features of a proper Lorentz transformation, and they are both preserved by composition. Now let's talk about time dilation. This is the slowing down of the clock of a moving observer. Let's see how this works. Let's look at the invariant spacetime distance again. Assume that this spacetime interval is time-like. This means the negative of delta S square is positive. We define this as c squared times the square of delta tau, which is known as the proper time. But whose time is it anyway? Suppose a particle is moving across this interval in the frame of O', but is stationary with respect to O. We say that O is the rest frame of the particle. In this frame, the spatial position of the particle is unchanged, but the particle moves forward in time. Here, we can see that the proper time is really the time measured by O and can be regarded as the time experienced by the particle. We can factor out the square of delta t prime on the right-hand side to get a relation between the time of O and O prime. This factor is just the inverse of gamma square. Since gamma is always greater or equals to 1, 1 over gamma is less equal to 1. This implies that the proper time attached to a moving particle always flows slower than the time of the frame in which it is moving. Just imagine that the particle is carrying a clock, and delta tau is the time interval between the two ticks of the clock, experienced by the particle. This is always less equal to delta t prime, measured by O prime, where the two ticks of the clock do not occur at the same spatial locations. This is what we mean by time dilation. The phenomena of muon decay in cosmic ray experiments is a good example of this effect. In the lab frame, where the muon is observed to be moving at high velocities, its lifetime could be 5 times as long as when the muon is stationary. Now, let's discuss the effect of length contraction. This is another consequence of the Lorentz transformation. Once again, we look at the invariant distance. Let's assume that this displacement runs from event A to event B and is space-like. Suppose that in the frame of O, A and B occurs simultaneously in time, and there is only spatial displacement between them. This is possible because we have assumed the displacement to be space-like. Now, let's relate the spatial distances measured by O and O'. We shall assume that O is boosted with respect to O'. We can then express the time part of the displacement in O' in terms of the displacement in O, which is purely spatial. On the right-hand side, let's multiply and divide by V. The term in the blue box is the dot product of the spatial displacement with the unit vector along the velocity. This is the displacement parallel to the velocity. Substitute this back into the equation above. Let's set this relation aside for later reference. Now, let's take a closer look at the spatial displacement in O' using the Lorentz Boost. Again, delta x0 is 0. Using the fact that lambda ij can be broken down into a projector along the velocity and a projector orthogonal to it, we have this says that the perpendicular component of delta x' is just the same as the perpendicular component of delta x. And therefore they should cancel in the equation above on either side. Now we can relate the parallel spatial distances measured in both frames. And we end up with this result. Let's see what this means. Let's assume that observer O' is carrying with her a meter rule, and that this ruler lies along the direction of relative motion. By our convention in defining the Lorentz Boost, O travels at a velocity of v with respect to O'. Therefore, conversely, O' travels with a velocity of minus v with respect to O. Delta x' in this case is 1 meter. And suppose, to measure the length of this meter rule, the observer O fires off 2 firecrackers simultaneously at both ends of the ruler, as O' is moving past him. By measuring the distance between the burnt marks on his reference frame, O should measure the length of the ruler carried by O' to be less than 1 meter, according to our result. This is because 1 over gamma is always less than 1. This is the effect of length contraction. It is the shrinking of a moving ruler as measured by a reference frame that the ruler is moving in. What does this mean from the perspective of O', the observer carrying the ruler? While O says O''s ruler has contracted, O' says O did it wrong. He didn't measure both ends of my ruler at the same time. This can be seen from the equation we have saved earlier. From the perspective of O prime, the time interval between the two events is not zero. One firecracker goes off earlier than the other. Like so. As you can see, the effect of length contraction is closely related to the relativity of the simultaneity of events. Now is the time we explain the causality paradoxes mentioned earlier that would occur if a particle is allowed to travel across a space-like interval. Suppose that the interval in question spans from point A to point B. To make our point, let's look at this in three different reference frames, O, O', and O double prime. Assume that in the frame of O, A and B occurs at the same time, delta t equals 0. And so the spacetime distance is entirely due to the spatial part. This is consistent with the fact that the spacetime interval is space-like. We claim that there is a Lorentz transformation between O and O', such that the time interval measured by O' is greater than 0. This means event B occurs after event A. And furthermore, there exists a Lorentz transformation that would bring O' to O double prime, such that the time interval measured by O double prime is less than 0. B occurs before A instead. This is the source of the causality violation we have pointed out earlier. If it is possible for a particle to travel between this space-like interval, then one could imagine a setup where a switch is pressed and a particle is fired from A and detected at B. And upon detection, a light bulb will light up. This will be what O' observed, and the physics of this sequence of events will be clear to her. Whereas from the perspective of O double prime, he will see the light bulb lights up at B spontaneously. Then after some time, a switch is pressed at A, and this will occur 100% of the time when the light bulb lights up. O double prime will then be forced to conclude that lighting up the light bulb causes the pressing of the switch, which will make no sense at all. This is the causality paradox. Now let's find the relevant Lorentz transformations. Assume that lambda and lambda prime are both Lorentz Boost, no rotations involved. To keep things simple, let's also assume that all spatial displacements, as well as the Lorentz Boost, are along the x-axis. First, apply lambda to the displacement measured by O to get the displacement for O'. Here, we introduce beta as the velocity ratio to keep things compact. Doing the multiplication, we have we require the time displacement measured by O' to be positive. This is always possible because we can just set beta to be in the same direction to delta x. Next, we apply a suitable lambda prime to get into the frame O double prime. We can set delta t double prime to be less than 0, as long as beta plus beta prime is opposite in sign to delta x. This is always possible with a suitable choice of beta prime. To put things more concretely, assume delta x to be greater than 0 and choose beta to be positive. The first condition would be satisfied. Then choose beta prime to be negative with a magnitude greater than beta. The second condition would also be satisfied. Thus we have found two observers, O and O prime, who would have come to opposite conclusions on the causality of events. This is the causality paradox, and is the reason why a particle could not travel along a space-like trajectory. Next, we move on to another standard result in special relativity regarding velocities addition. The question that concerns us is this. Suppose O is moving at a velocity v relative to O prime, while O prime moves with velocity u relative to O double prime. What is the velocity of O relative to O double prime? This is an important question that has to do with the principle of relativity, in which the speed of light has to be the same in all inertial reference frames. According to pre-relativity physics, the speed of O relative to O double prime would just be v plus u. But assuming that both velocities are along the same direction, if v equals the speed of light and u is non-zero, then the resulting velocity would have to be greater than the speed of light, violating the principle of relativity. The following exercise is to derive the correct rule for velocities addition that is consistent with relativity. We shall do this for the general case, where the velocities need not be in the same direction, using the general form of the Lorentz Boost. Let's look at the Lorentz Boost from O to O prime. And from O prime to O double prime. In components form. Now we focus on a point which is stationary relative to O. This is the reference point that moves with O relative to O prime at the velocity v. Expanding out the sum over nu into time and space components. The velocity O relative to O double prime is simply given by W. Both the numerator and denominator on the right-hand side can be given by the equation above. We can divide out the delta x naught on the right-hand side. Let's evaluate this term. First, let lambda ij of u x on v, then multiply by 1 over c gamma. For the first term, we have where the usual dot product for spatial components is used, and the second term This expression is the correct way to sum the velocities in the context above. This will be consistent with the principle of relativity, where the speed of light is the same in all inertial frames. Because we have derived this using the Lorentz Transformation, which is itself derived from the constraint of this principle. From this general result, we can verify the more familiar case, where all the velocities are in the same direction. This is what you will usually find in textbooks. You can easily check that if either u or v is equal to the speed of light, then w must also be equal to the speed of light. In this section, we tie up some loose ends regarding the Lorentz transformation. Let's calculate the inverse of a Lorentz transformation, which is defined like so. Our convention here is that a lower index is always contracted with an upper index. Remembering this will make the operations easier to follow. We can calculate the inverse directly from the invariance equation. Multiply both sides of this with lambda inverse, contracting through the index alpha. Now multiply by eta, which is its own inverse. This gives lambda inverse in terms of lambda, which is the result we are after. This is the point when we give actual significance to the raising and lowering of indices. Before, we have mentioned that a matrix with a raised or lowered index is merely a notation. It is really still the same matrix. Now we define the original lambda with the inner index raised and the outer index lowered, and then define another object in terms of this by lowering the upper index with eta and raising the lower index also by another eta, but which has two upper indices. Both etas are the same matrix. This new object is equal to the inverse of lambda. We shall encounter such raising and lowering of indices very frequently in subsequent lectures. Usually, an object is defined with a certain original arrangement of indices. From this, we may derive new objects by raising or lowering indices using ether, as we have done here. For example, take the invariant distance. We can write this as the contraction between an upper index displacement and a lower index displacement. We can define this in terms of the upper index version, lowered by ether. As a result of the invariance equation above, the contraction of an upper index object with a lower index object automatically gives us something that is invariant under Lorentz transformation. Let's work out how the lower index displacement transforms under the Lorentz transformation from the transformation of its upper index counterpart. In any inertial reference frame, the raising and lowering of indices are done by the same ether. From our earlier result, this is just the inverse transformation. Now it becomes obvious why the contraction of an upper index with a lower index object always gives us an invariant quantity. Lambda is always cancelled by its inverse. Objects that transform in the same way as the upper index displacement are known as vectors, while those that transform like the lower index displacement are known as dual vectors. Alternatively, upper index vectors are known as contravariant vectors, and the lower indexed ones are the covariant vectors. This is the convention that we will be using. But what about an object like ether? Any multiple index object that transforms under Lorentz transformation in a linear way, like what we have here, is known as a tensor. We can write the equation above in another way, bringing the lambdas to the other side of the equation, which turn into their inverse. This transformation then fits the pattern of the covariant vector, so ether is a covariant tensor. It's just that ether is a very special tensor, which is invariant under Lorentz transformations. So it is both a covariant and a contravariant tensor. In general, a tensor could have a mixture of both upper and lower indices, and these transform under Lorentz transformations according to the rules in the blue boxes. We shall discuss these objects in greater details in the next lecture. As an exercise, let's calculate the inverse of the general Lorentz Boost using the formula above. This is a simple exercise if we know what exactly does ether do. It multiplies whatever carries the time index by -1 and leaves all the spatial indices alone. From this observation, it is apparent that only the elements of lambda, which carries only one time index, gain a minus sign, while the rest of the elements are unchanged. These are the results of directly applying the relation underlined red to the yellow box. By comparing the red and yellow boxes, we can see that lambda inverse is actually just lambda of minus v. This just confirms something we knew intuitively. If O is moving at velocity v relative to O prime, then O prime must be moving with velocity minus v relative to O. If both reference frames have the same spatial orientation. Here's a summary of important results in this lecture.